In example 3, we have a reinforced concrete beam of width B equals to 330 millimeter. This should be millimeter. And the overall depth of the beam is 520 millimeter. And we have the beam is reinforced with 6 N28 bars on the tension side. So there are 6 reinforcement, as you can see. 6 normal ductile reinforcements, and the beam is subject to the maximum bending moment M star of 320 kilonewton meter due to the combination of dead load and live load. The concrete is 32 megapascal compressive strength, and now you are required to draw the strain and stress profile for the beam, find out the maximum flexural moment capacity or ultimate moment capacity MU for the beam. And as a consulting engineer, you also have to verify if the beam satisfies the strength and ductility requirements according to AS3600 as well. So let's first draw the stress strain profile for the beam, and let's proceed from there. So here there are 2 layers of N28 bars, 3. So when we draw the strain profile, we can draw at the center of those 2 layers, so that we don't have to do 2 strains for the steel, 2 layers of strain. So we'll do at the center of this reinforcement, which is at 90 millimeter from the bottom. So we'll draw it strain profile for all of the 6 at the middle one only. So now drawing the strain profile here, and that's your strain profile, and this is your neutral axis depth. Here this is the strain in steel, which is epsilon ST. Crossing strain of concrete is epsilon CU 0.003, and this is the depth of the neutral axis, which is KUD, and that's what we already have. And now let's draw this. Now this is the strain profile again. Now let's draw the stress profile. Now similarly the force one. Now for the force profile, compressive force is acting at this point and the tensile force is acting at this point. So first we need to find out what is the effective depth up to the center of the reinforcement. So the effective depth in this case is up to the center of the reinforcement, up to here. So let's find out what it is. So overall depth D minus the effective cover is 90 millimeter. So that means 520 minus 90. So it is 430 millimeter. So we now know the effective depth. And for compressive strength of concrete as 32 megapascal, we know that alpha 2 you can find out using the equations that we know is 0.8, and gamma using the same equation like before, it is 0.89. This is from AS3600 8.1.3. Now we have 6 steel here, so 6 steel of N28 bars, so that means the total area of steel is 28 millimeter bar. So that means it comes out to be as you can see here, this beam is quite heavily reinforced, so there is quite a lot of reinforcement at the bottom in the tension side. Now, as we did in the previous question, we will first assume that it is a tension failure, and then we will proceed and find out the KU and check the steel strain and whether it is yielding or not. So we'll make the assumption first and then check it whether it's correct or not. So proceeding exactly like example 2. So when we assume that it is a tension failure mode, so that says that your strain in the steel is already greater than the yield strain 0.0025, and that in turn implies that the stress in the steel is equal to the yield strain, that is 500 megapascal. So we are proceeding with this assumption. We will have to check whether this is correct or not as we proceed. Now again, equating the horizontal forces, the horizontal forces C has to be equal to T. So equating the horizontal forces, and putting the values of C and T. Again, C is the volume of the equivalent stress block. We are assuming that it is a tension failure, so the steel is already yielding. That means the stress is already FSY. So we can find out KU like we did before. The area of steel we found out is 3694.51, and steel is yielding. That means FSY is 500 megapascal. Alpha 2 is 0.802 something, and FC dash is 32 megapascal. Gamma comes out to be 0.89, and KU is what we have to find, and D is 430 as we found out, and B is 330. So with that, if you compute the KU, it will come out to be 0.57. Right from the KU itself, we can see that KU is greater than the balance failure KU. Note here that KUB for balance failure as we computed in the lecture is 0.545. So this KU is greater than KUB. It is greater than KUB. That means it is compression failure. We can see right from there as well, but we will proceed to find out the actual strain in the steel and see how it comes out. So let's check the strain in the steel. Again, using the strain compatibility question, epsilon ST can be written in terms of epsilon Cu, which is the crushing strain of the concrete, is 1 minus Ku divided by Ku. So this is a strain compatibility question. Crushing strain of concrete is 0.003, and we just computed Ku as 0.57. So if we calculate this one, epsilon ST or the steel strain comes out to be 0.0023. Now, is the steel yielding? We know that epsilon SY, the steel yield strain is 0.0025. But this steel strain at this point is coming as 0.0025. That is epsilon, it is less than epsilon SY, which implies that the steel is not yielding. It means that our assumption that the tension failure mode occurs is not correct. So the assumption that we started with, that the tension failure occurs, is not correct for this particular example. So we have to redo this question again. And let's consider it as a compression failure, and let's proceed with that. So now proceeding it as a compression failure, because we know now that it is not a tension failure, so proceeding it as a compression failure. Now considering compression failure mode, and exactly doing C equals to T to find Ku as a compression failure, but we will see that how to proceed with that. Now the thing to note here that in tension failure we took the stress in the steel equal to Fsy, but when we are considering that the steel has not yielded yet, so we cannot take sigma st equals to Fsy, because the steel is not yielding. Sigma st is not equal to Fsy, so we cannot consider that the steel is yielding. So what we do in this case is that we will write area of the stress in the steel in terms of the strain in the steel. So let's write that. So AST. So we are writing in terms of the strain in the steel using Hooke's law. Now we can again write the strain in the steel using the strain compatibility equation in terms of the strain in the concrete. Therefore alpha 2 FC dash gamma Ku B D should be equal to this one. Now what we do is we proceed with solving this equation. So write down all the parameters here. So alpha is 0.80, FC dash is 32 megapascal, gamma is 0.89, is 400, D is 430, and B is 330, and area of steel is 3694. Young's model of steel is 200,000. Epsilon C is 0.003. Now this question is quadratic in Ku, so we can simplify it and we'll see that it is quadratic in Ku. So just rearranging the equation. So you can see that this equation once simplified is a quadratic in Ku, and we can solve this equation to find what is the value of Ku. So therefore Ku is 0.553. Once we solve this quadratic equation, Ku comes to be 0.553. Now again we have to check whether our assumption was correct or not by checking this strain in the steel. So how do we check the strain in the steel? Using the strain compatibility equation again, it is 0.003 1 minus Ku divided by Ku. So this is the trussing strain of the concrete, and 1 minus Ku we just computed is 0.553 divided by 0.553. So once we compute this one, we see that the strain in the steel, the actual strain in the steel, comes to be 0.0024. Let's write it here again. So we see that it is less than epsilon sy, and which is correct because we started here in the second part. We started with an assumption, with considering that it is a compression failure mode, that is the strain in the steel is less than epsilon sy for a compression failure mode. Therefore, the beam is failing in compression failure mode, and our assumption is correct. So assumption is okay. Now, as it is correct, so we can proceed to find out what is the moment capacity of this beam using the moment equilibrium equation. So now taking moment about C. So we have the force diagram here, as you know. This is the force C, the tension force acting at T, and the lever arm is Z. So we are taking the moment about point C here again. So it is ultimate moment capacity is T multiplied the lever arm Z, and T is AST into sigma ST. Remember, the steel is not yielding, so we cannot write FSY. And Z is, again, the lever arm is D minus gamma KU D over 2. So we have to write steel in terms of steel stress in terms of strain again. And the area of steel is, we already know, 3694.51 millimeters square. And steel stress we do not know yet, so we have to still write in terms of strain, which we already know. So it is this is written as ES multiplied by epsilon ST, which we already know, epsilon ST. So ES is 200,000 multiplied by epsilon ST, we just found out as 0.0024. And we know the rest. 430 is your effective depth, gamma is 0.89, KU is 0.553, new computed KU, and D is your 430 millimeter, and that gives us your ultimate moment capacity comes as so the ultimate capacity for the beam comes as 574.9. Now with this you can find out what is your design moment capacity as well. For that you will need to know what is your strain reduction factor. So to find, this is one question that was asked, the ultimate moment capacities. Next, to find the design moment capacity, is strain reduction factor multiplied by mu. So phi is obtained from AS3600 table 2.2.2 for flexure. So as you can see, for AS3600 table 2.2.2 for flexure, that is for bending with without axial tension, for N class N reinforcement, as the question says, phi is given by, it should be between 0.65 and shouldn't be greater than 0.85. Now putting the value of KU here, 1.24 minus 13 into KU is 0.553 divided by 12. So if you find out this one, it comes out to be 0. So it comes out as the minimum one, we have to use 0.65. We have to use 0.65 because that's the minimum KU that we have to use for this equation. So taking KU as 0.65, we can find what is the design moment capacity. Therefore, phi mu is 0.65 multiplied by 574.9, which is mu. So that gives us the ultimate moment capacity as 373.7 kilonewton meter. Now we know that in the question it is given that the load in the beam is M star is 320 kilonewton meter. So the total external moment that is acting on the beam is 320. That means phi mu is still greater than M star. So it does satisfy the ultimate strain design equation. So strain requirement is satisfied because your design moment capacity is 373.7, but your external moment, which is given in the question, is only 320. That means the beam satisfies the strain requirement. However, one thing to note here is that it is a compression failure mode because the steel strain is not yielding, and we also found that KU is 0.553, which is greater than the balance failure mode 0.545. So we know that KU is 0.553, which is greater than 0.545 for balance failure. And we also saw, of course, that epsilon ST is less than epsilon SY. Steel in tension is not yielding. Which leads us to compression failure mode. And we know that it is a brittle failure and should be avoided. That means it does meet the strain requirement, but the ductility requirement is not satisfied. So we see that the beam is heavily reinforced, over reinforced in fact, and it goes into the compression failure mode, making the beam very brittle. So it will fail very abruptly without warning to the occupant, so which is not desirable. So this beam, even though it satisfied the strain requirement, it doesn't satisfy the ductility requirement.